Hello everyone and welcome to Advent of Cyber Day 17, and today's task title is I taught a C2 tat, and if you don't know the reference,
I taught a putty cat.
So let's do a quick overview of the story here. So congratulations, you made it to day 17. The story, however, is just getting started. There are more things to discover, examine, and analyze. So up until now, we've worked with multiple events, including the prompt injection from day 1, log analysis, brute force, data recovery, exploitation, data exfiltration, suspicious drives, malware injection, pretty much everything so far. And over those days, we found a lot of anomalies, a lot of indicators of attack or IOAs, indicators of compromise or those IOCs. And in this case, Santa's Security Operations Center, the SSOC, needs to see the big picture to identify scope, prioritize, and evaluate these anomalies in order to manage the ongoing situation effectively. So the main theme of today's task is pretty much going to be zooming out. With everything going on, it's not feasibly possible to look into every single detail of every single log, every single packet capture. So we need to sort of take a step back and see that big picture, which is going to allow us to identify patterns more easily and more effectively prioritize our response. And in this case, you can see McSkitty decides to focus on network statistics. So when we're capturing all these network events, gathering all these artifacts, so it's a good choice to consider the artifacts that we're capturing on the network from the inside and outside, as well as the statistics itself, in order to see that sort of big picture and to come up with our next plan of action. So to access the machine, today we need to start the VM, and there's going to be a split screen available with this VM. So if we just click Start Machine here, it should open up in that split screen view automatically. And if for some reason it doesn't, you can just scroll up to the top of the page here and click Show Split View, and it's just going to open up in that side screen there. While this loads, let's just continue reading. So the SSOC, Santa's Security Operations Center, gives us a pre-configured VM for our convenience. It contains a fresh version of Silk, which is the System for Internet Level Knowledge, which is an open source network flow collection and analysis tool, which I'm sure we'll get to in a sec here. But it already has that tool pre-installed for us. And as for our learning objectives today, we're going to gain knowledge on the network traffic data format. We're going to understand the differences between a full packet capture versus a network flow, so sort of a more detailed capture versus a summary, which we'll get to. We're going to learn how to process the actual network flow data, as well as work with the Silk tool. And through that, we're going to get a hands-on experience in network flow analysis using Silk. Okay, so you can see our VM has started here on the right side. And what I'm going to do to make our lives easier and to make your life easier when you do this room, let's go under here under the View in Full Screen button here. So we're going to click on that, which is going to open this new tab, which is going to contain our VNC connection here. And what we can do is we can go back to the task, and then we can click this Exit Split View just to minimize this. So now that we just have the task in one tab and we have the full browser in the other one. So let's start off with a bit of theory. This is going to be, a bit of reading, a bit of background info, which is not always the most exciting, but it's very important to understand the concepts here. So with network traffic data, network communication and traffic are the natural behaviors of today's interconnected computing world. These behaviors represent a constant data flow of daily activities, including personal interactions and business transactions. The data flow offers invaluable network management, troubleshooting, incident response, and threat hunting insights. And you can see this table here, which is going to highlight the importance and the key differences and benefits of each of these aspects. So we have network management, which is, the whole idea of monitoring network performance, identifying where the bottlenecks are, and basically just ensuring everything is in order with resource allocation and quality of service. And then there's the whole idea of troubleshooting. So obviously having statistics and data on your network flow is going to help you immensely identify network issues, so latency or connectivity issues, as well as validating configuration implementations and changes, or seeing if something went wrong through a configuration change, as well as setting the performance baselines. So, what is normal, what should we expect to see in our network, which is going to come into play pretty much in all of these aspects as well. So then we have incident response, which is going to be that incident scope, that root cause analysis, as well as the assessment of all those compliance aspects. And then we have the ever-exciting threat hunting, which again is that proactive analysis for signs of suspicious or malicious patterns within the network. We're looking at potential threats, we're looking at anomalies, those indicators of compromise or indicators of attack. And then with that data, we can also look at behavioral analysis. So we can look at what is our baseline, what is our normal expected activity, and then what is abnormal, what is anomalous, right? So we can use that to detect intrusions as well as insider threats. So an important point here, so network traffic comes in various data types and formats. So you're probably more used to seeing packet captures or that PCAP format, which is also known as full packet captures. And full packet captures or PCAPs sort of provide that granular, raw, and comprehensive view of the network traffic. It's pretty much going to contain all the data of the packet, and it's going to present that in a ready-to-investigate format. So if you ever heard of the term deep packet inspection, it's actually opening up packets and looking at, the data and the payloads inside of them. And because of that, it's very important. So it's basically invaluable for artifact and network level operations if you want to understand what is happening at the packet level. But of course, it also comes with some costs. So it's very resource intensive. You need to have storage, processing, as well as analysis capabilities to sort of provide that comprehensive, in-depth, detailed insight into the network traffic. So again, while PCAPs are very useful for that detailed analysis, they're not super practical for scalability or fast analysis situations, as they include the full payload, all of the details, so it can sort of become a pain when large amounts of data needs to be analyzed quickly. So really what we're looking at when we want to do fast, quick, summarized analysis, we need to process the data in a format that doesn't enclose all of that payload data, all of that detail that we don't always need when we're looking at a high level. So that's where network flow data comes in, which is a lightweight alternative to PCAPs. You may also hear it referred to as the NetFlow format, which is a telemetry protocol developed by Cisco, and it focuses on sort of that metadata. So we're taking a step back, zooming out a bit, and really only providing a summary of the traffic. So if you see the analogy here, think of how call details appear on your phone bill. You're not going to get all of the contents of your phone message. You're not going to get a transcript of everything that was said, but you're going to get sort of that metadata, that higher level, when the call took place, how long did the call last, who was the source, who was the destination number. But once again, there's going to be no packet content details, there's no message content details in that format. So storing, processing, and analyzing that data is a lot easier than when it comes to PCAPs. Now, if some of this stuff is a bit over your head, no worries. Take a look at the network fundamentals module here. And this is going to basically, this is going to cover everything from what is networking from that beginner level all the way to the OSI model, looking at packets and frames and how they differ, and basically how information is transmitted across the network. So this is a perfect module if you want to do some more reading or if you want to understand more before we continue. But fear not, as this task is completely guided. So even if you don't know, what we're talking about here, you're still going to be able to follow along and figure out what we're doing. So let's take a closer look at the differences here. So with packet captures, again, we're getting that detailed granular data. We're getting, contain the packet details as well as the payload. If we're looking at the purposes or what do we use this for? Well, deep packet analysis. So again, we're getting that high visibility, at the expense of cost. So resource cost, storage cost, as well as the actual effort to analyze, captures at a detailed level like this. And there's also the level of encryption here. So, even if we're capturing all of the network details, it can still be encrypted. And it should be. So it's going to require some additional processing, some, deep packet inspection in the middle, sort of sitting between the networks, so you can actually decrypt and understand what is going on at that detailed level. On the other side here, we have the network flow. So we're getting that summary data, and again, it doesn't contain the packet details or the payload or the sort of the body of that packet. So again, what is the purpose? Well, if we need a summary, we need to get quick analysis, we need to do statistics. It's perfect for that because it provides that high-level summary of the big picture. Encryption is not an obstacle because we don't even capture the packet payload at that point. But with the cons, again, we're not getting that payload. If we need to do more detailed inspection, we would have to resort to PCAPs, which is why it's often useful to use both, right? Use NetFlow for the big picture, figure out where the anomalies are, look at the patterns, and then from that point, we can sort of drill in to the actual packets and look at what is going on from that level. So, and you can see this table here basically outlining what is the difference, the actual values, how they differ between the two. So you can see for the PCAP, we're getting application layer protocol details, as well as the packet data and the payload, as well as just some other stuff you'd expect to see. If you ever look in Wireshark, you can probably see this information if you have a PCAP. You're going to get that lower level link layer information, the MAC addresses, the source and the destination, as well as the IP and port. And then on the network flow format, we're going to get some of this information, but it's going to be more summarized, more abstracted. So we're still going to get the IP and the port information, the source and destination. We're going to get the time details, when the packet was sent, the duration, the end time, but we're not going to get the actual details of the application layer protocol. And then obviously we're not getting the actual contents of the packet data itself. So now that we sort of know what the difference is a little bit, we can take a look at how to actually collect and process network data. So network data collection and processing typically involves using network monitoring and analysis tools such as Wireshark or utilities like Tshark or TCP dump, which you might be more used to. And we use these tools to collect information about the traffic on a network and then analyze that data to gain insight, to do troubleshooting, or to conduct blue and purple team operations. And there are also different products and system-based solutions out there that we can use and leverage to help us collect this network data in the flow format. And the specific tools and methods that you use to collect this information often depends on the size and complexity of your network, or the size of your organization, or your organization maturity. All those factors kind of go into what tool set or methodologies you're going to use. And if you don't know what Wireshark is, there's a fantastic module that TryHackMe has on Wireshark, which is going to go over the basics as well as packet operations, traffic analysis. So if you want to get all of the need-to-know functionality of Wireshark, or you just want to brush up a bit, definitely check out this module. So in this case, it looks like we have the PCAPs and the network flows already recorded and captured, which is great. But the available data needs to be more organized and ready for analysis. Okay, that's where we come in. Okay, so we can collect network flows from endpoints and network devices in the same way that we can collect full packet captures, right? But it's also possible to convert those PCAPs or those full network captures into network flows if we need to, take a quick look at the statistics or do some of that high-level analysis. And there are many open source tools out there that are going to help us do that. But fortunately, in this case, the ever so handy ELF Forensic MacBlue has already converted all of the network traffic data to binary flow format, so we can just focus on the analysis portion. And for that, as you can see, we're going to be using Silk. So as I briefly mentioned earlier, it stands for the System for Internet Level Knowledge Tool Suite, and it was developed by the Cert Situal Awareness Group at Carnegie Mellon University's Software Engineering Institute. And you can almost think of it as like a library that includes different tools and binaries that we can interact with to do different things, such as the collection, the parsing, the filtering, and overall just the analysis of the network traffic data. So in this task, we're going to experiment using the Silk suite, or that's tool set that we have available to us that's already installed, on the binary formats to help the Santa Security Operations Center team achieve their goals. So it has two main parts. So we have the packing system and the analysis suite. So the packing system supports the actual collection of those multiple network flow types. So we have IPFix, which stands for the Internet Protocol Flow Information Export. But for this case, you don't need to worry about that. And then on the other hand, the analysis suite, which is what we're going to be interacting with, contains all the tools necessary to carry out the various operations. So we can do things like listing, sorting, counting, different filtering, as well as quickly generating statistics on our NetFlow records. So the virtual machine contains a binary flow file, suspiciousflows.silk, in the home Ubuntu desktop directory. And I think we see this on the desktop here. Yeah, perfect, right here. And if we wanted to open up the terminal, because we're certainly going to be needing it, let's just cd over to the desktop and run an ls, and you can see we have suspiciousflows.silk right here. And that's what it tells us to do right here. So cd over to the desktop and list of directory items with ll. If you don't know what ll is, it's basically just like writing ls.l. It's just sort of an alias for that, just a quicker way to get that information. And with this setup done, it looks like we're ready to go. So the next step is discovering the details of the pre-installed Silk instance in the VM. So use the commands provided to verify the Silk suite's installation. Use the following command to verify and view the installation details. So that's just going to be silk_config, and then we're going to provide it the TACV or that V argument. So we have access to this tool, silk_config, I believe it was. And if we just run which silk_config, you can see this is actually a binary or an executable binary that we have on our system. And it's within our path, so we can just call silk_config, and it's going to run for us. So we can provide that TACV option for the version information. And you can see here we have silk_config, we have a bunch of information here about the different configurations, we have some copyright information, but right up here at the top in the first line we have Silk version 3.19.1, and I believe that is the first answer in this task here. I'm going to scroll down to the questions here. Which version of Silk is installed on the VM? Well, we just answered that. It's going to be 3.19.1. Perfect. All right, let's continue. So let's move on to file flow properties with Silk Suite, and that's going to be rwfileinfo. One of the top 5 actions in packet and flow analysis is overviewing the file info. So Silk has a built-in tool that we can run called rwfileinfo. Not sure if it's read-write file info or something, but that's what it's called. And we can use it basically just to print information about the binary Silk file that we're going to analyze. So it's going to do that by reading the file's header, as well as looking at the different data blocks in the file, which is not something we need to worry about. We just need to worry about the syntax here. So it's going to be rwfileinfo, and then we're just going to provide the path of the file. So in this case, rwfileinfo suspicious, and I'm just going to hit tab to autocomplete that there. So if you're wondering how I typed that so quickly, well, I didn't. I just started typing it and hit tab, and that's going to autocomplete the name there. And there we are. You can see we have the different information or the different metadata about our Silk binary file here. So we have the format, we have a version number here, as well as different compression information, header length, record length, as well as the Silk version and the count of the actual records. So it looks like we have 11,774. And I think that is the answer to the second question. So scrolling back down here to the second question, what is the size of the flows in the count records? Well, as we found here by running the rwfileinfo command, we have 11,774 count records in the total file. Excellent. All right, let's go back. All right, let's talk about reading the actual flow file itself. So we have this utility, this tool, rwcut, and that's basically going to read the binary flow records and print those selected by the user in text format. So for example, we can open and print all of the records without any filters on any of the parameters, and it's basically just going to output every single record in the file. So to run that, the syntax is rwcut, and then once again, provide that file name. So we're probably going to get a lot of output here. Yeah, there we go. So it's all not very helpful with all of these records just displayed like this in the terminal. So that's why we're going to need to filter and do some more interesting things to make this more readable. So therefore, we need to manage rwcut's tool output size using the following command. Okay, so we can provide the --num--rex equal 5. So that's going to limit the amount of records that are present in the output to 5. So we're just going to get the top 5 records, or I guess the first 5 records in the sample. And then we can also view the bottom of the list if we just change numrex to tailrec equal 5. So let's try that. Just going to clear the screen here. I'm going to just go up twice to find that previous command, and then I'm just going to add the --num--rex. We're going to equal 5, and we should just get 5 results here. Yep. So you can see it's kind of output in this table format. So we have this first line here is going to be the table headings. So we're going to have different columns here for the source IP. These are just default columns. Destination IP, the source port, destination port, the protocol, which we'll get to in a second, the packets, the bytes, the flags, and so on. So, okay, so we learned how to read flows with rwcut. Now let's discover the different filtering options we have. And the way to think about this is it's more so a visual filter. So we can actually control which columns are going to be returned using the fields parameter here, the --fields. And you can see there are different options that we have. So we have source IP, destination IP, the different ports, the duration, the start time and end time, as well as some more. So let's try this one here. So we're just going to provide basically the same thing where we're going to pull the first 5 records in the sample, but we're going to filter the columns based on the protocol, the source IP, the source port, destination IP, and destination port. Okay, so I'm going to clear this, and we're going to bring up this command again, and then all we're going to do is provide the fields filter here. You can sort of see it's like key, equal sign, and then a value pair. So what we need to do is provide these comma separated values. And I'm just going to copy this because I'm going to try to remember that and fail miserably. So let's copy this using the, on the side here of the VNC console. We can just paste in what we want to paste. Now that we have that on our clipboard within the VM here, we can just do paste. And you can see we have the different columns here ready to go. So let's just run this. And there we go. Similar output as last time, but you can see we actually manipulated which columns are being returned. So we just have the protocol, the source IP, the source port, the destination IP, and the destination port. Okay, so this is what I was talking about the protocol column. So you can see it's all in numeric values, right? Nothing here is a string other than the names of the columns. So even under the protocol here, you would expect to see something like ICMP, UDP, TCP, but we're just getting binary data here. We're just getting numbers, right? So what does this mean? What does 6 mean? So Silk highlights protocols in that binary format. So 6, or you might see 17 or 1, not in the keywords like I mentioned. So if we look at this little hint here from Elf Forensic McBlue, it mentions that in the forensics aspect of network traffic, every detail is represented by numerical values. This makes it a lot easier to work with and is also more consistent. And these values are actually assigned by the IANA, which is the Internet Assigned Numbers Authority, which, if you haven't heard of them, they also do things like they oversee the public IP address allocations, the AS numbers, all sorts of things with DNS as well. And in this case, they've assigned different numbers that pertain to the different protocols. So you can see here, ICMP traffic is going to be 1, which we don't see here. We see 6. So, TCP traffic is going to be 6. UDP traffic is going to be 17. So this might come in handy later. So let's just keep that in mind. And you can see what is the start time or the S time of the 6th record in the file. Well, we actually can't answer that here because we're only pulling back 5 records. So how can we change our command to make this work and get that 6 records? So let's run rwcut again, and we're going to provide suspiciousflows.silk. And once again, we're going to provide that fields parameter. And the field that we're pulling back here is S time. So we can just provide S time. We don't really need the context around the other columns at the moment because we're just trying to pull back that answer. And then for the number of records, we don't want to pull back everything, but we also don't want to pull back 5, which we've been doing. We want to pull back at least 6 so we can see what that last value is. So let's copy this 6th value here and see if that is the correct answer. There we go. There it is. Perfect. We are moving along here. Let's go on to some more filtering. So with the actual rwfilter command, what this is going to do is basically allow us to implement conditional and logical filters to the actual records that we're extracting. So, not dealing with just the columns, we're actually making some filtering and making some logic on what we're pulling back. So this is very useful for cutting down the amount of records that we're returning. And that's why it's probably one of the most useful commands here. So it comes pre-built with multiple filters that we can use for each column in the sample that we're working with. But there is one caveat to it, and it's that the output is expected to be post-processed. So what that means is that it doesn't actually display the contents in the terminal. We have to tell it to do that in a specific way with the syntax. And it's most commonly used or combined with rwcut so we can actually view the output. So that's what we're going to have to do. But you can see the base syntax here is going to be rwfilter and then the file name. So let's try that and you might have a better idea what we're talking about. So if we run this, we're going to get an error. So you can see no output was specified. So we're actually not getting that output. And I should say we also didn't provide any filtering options, so that's also why we're getting an error here. So what we want to do here, for example, is to start filtering all the UDP records using the protocol filter. And if you remember, UDP in that binary format stands for 17, so that's the number that we're going to need to filter by. So you can see the syntax here is going to be rwfilter, we're going to pass in the file, and then we're going to pass in the filtered arguments. So you can see proto stands for protocol. So we're going to pass that in as its own argument, and that key value pair is going to be proto equals 17 to pull back those UDP records. And then note this second argument here, which is the pass equals standard out. So we actually need to include that so we don't get that error message, and that we can then pass it into rwcut using the command line pipe option there. So we're actually taking the output that we receive from this, this argument is telling us to actually give us a standard output, and then we're piping or parsing that into the rwcut command, and we're limiting the number of records to 5. So you can see we're kind of getting, a little bit more complex here. We're combining two different tools, two different syntaxes of tools, and two different, sets of arguments that we can provide. So you can see how, even at this basic level, how powerful this can be. So let's figure out how we're going to run this. So I'm just going to copy this again and then paste this in and make sure that we fill in our file name here, and we should be good to go. Okay, perfect. So you can see we took that output, passed it into rwcut, and we are limiting to 5 records. And we are pulling back specifically 5 records, the top 5 records, where the protocol is equal to UDP traffic. So here's some of them that we can use. So again, proto for protocol, the possible values are 0 to 255. Remember, it's that binary format. But we can also do port filtering. So we can do any port, or we can do a specific source port or destination port. And again, the possible values there are, the valid number of ports that exist. For the IP address, we can put basically any IP address for the source or the destination. And then we also have volume filters, so the number of packets or the number of bytes. Okay, so we have the essential tools now to get that big picture view. And now we can also sort of start zooming in on events of interest using the rwfilter. So let's discover some statistics that help the SOC team check out what's happening in the network. So for the next question here, what is the destination port of the 6th UDP record? Okay, so we can actually just sort of alter what we're returning here to 6, and we should get that answer there. So you can see the question, what is the destination port of the 6th UDP record? Well, let's count down to the 6th record, and let's look at the D port column there, which is going to be destination port. And you can see the destination port here of the 6th record is 49950. So I'm just going to copy that, and we'll paste that right into the answer there. Okay, so we looked at reading the output, we looked at filtering the output. Let's do some even more high-level stuff, that more abstract stuff, and look at statistics. So we can speed things up a bit for, a quicker and more automated overview of the network traffic. So we're going to use a new tool here called rwstats, and the syntax is going to be pretty familiar at this point. So we're going to call the tool, we're going to provide the file name, and then we're going to provide the fields argument here, and that's basically going to specify the field on which the statistics will be based on. So in this case, we want to provide the destination port, meaning that all of the analysis will focus on that column or the destination port column in the network traffic data that we pull. And then we're going to provide some values here. And basically the values is going to specify which metrics we want to extract for each destination port. So in this case, the records or the number of records, the number of packets, the bytes, how many bytes, the source IP distinct, which is going to be the number of distinct source IP addresses, as well as you can basically follow along for the DIP, which is going to be the distinct number of destination IP addresses. And then count 10 here at the end. That's just another way that we can do to limit the top 10 entries that we're going to pull. So it's a bit like the numRex argument that we used before, but in this case, it's going to pull the top 10 values. Okay, so I'm just going to run that now, and you can see we're getting some results here. So we have 4,160 records, 4,333 packets, but the most interesting values here that we get are the actual percent values here. So you can see the percent of records for DNS is 35%, which is a lot more than port 80. Which is still up there. So we have some HTTP traffic as well. And then you can see after that, we're basically dropping off to like 0%, 0.0%. So in this case, it's safe to say that we're looking at primarily DNS and then subsequently some HTTP traffic as well in this set. So again, to remember, the flow analysis doesn't focus on the deep packet analysis that you're used to working with in Wireshark. The aim here is to have the statistical data from a high level to help, in this case, help McSkitty foresee the boundaries of the threat scope. So again, let's go down to this question here, which is asking what is the record value percentage for port 53 or DNS? And again, we actually just looked at this. It's 35.3320, whatever, repeating. So we can just copy that value and paste it in here, and we're going to get the correct answer. Excellent. Okay, it's time to assemble the tool set and start hunting anomalies. Awesome. Okay, so we have all the necessary tools, and we've sort of covered all the different syntax, all the different commands that we're going to be running. Now it's time to use what we learned to save Christmas. And we can do that by listing the top talkers on the network, or I guess the most frequent IP addresses that are communicating over the network. So to do that, again, we can use our rwstats to get a quick percentage or a quick statistic on the different values that we're pulling here. So again, we want to list the top IP addresses that are communicating. So in this case for fields, instead of the destination port, let's look at the source IP address. And for the values, we want to look at bytes because that's going to be, how many bytes are being sent over from that IP address. And then the --top here is going to just pull the top records. Okay, so if we run this, we should get an output here with a bunch of IP addresses under the source IP column. So this is the column that we're filtering on. And you can see the top result here is 175.219.238.243. And because we grabbed that bytes column, we have access to the percentage of bytes here. And you can see about half of the network traffic is coming from this IP address. And you can see in second place here, we have this .221 address with about 32%, and then a third address here with about 10%. So in this case, this is going to be the IP that is communicating most on the network. Okay, so let's list the top communication pairs to get more meaningful, enriched statistical data. Okay, so for the communication pairs, let's look at the correlation between the source IP and the destination IP. So we can just change our original query a little bit here. And instead of source IP for the fields, we want to provide a second one for destination IP. And then for the values, we want to actually pull the records. We want the number of records. The bytes, we also want that as well. And let's also grab packets. Okay, that looks good. Let's run that. You can see here the top communication pairs. So we have the source and the destination IP. So if we hop back here, so we can take a look at the bytes and the records columns. So these columns are going to highlight where the majority of the traffic originates. Now, the top communication pairs or the top talkers stand out since they are creating the majority of the noise on the network. So in this case, this IP address, the 175.175.173.221, communicating with 175.219.238.243. You can see the amount of records here and the amount of bytes that are being sent over. In second place here, we have 243 communicating back to 221. So it looks like this pair here of IP addresses is communicating back and forth the most on the network. So remember what we found in the last part of the rwstats. The high traffic volume is that DNS traffic, so that port 53. Let's focus on the DNS records and figure out who is involved. Okay, so let's just change our filter here a little bit. What we want to do is look at all ports, and we want to specify 53. So because we want to look at destination or source, we're going to do all ports here. And once again, we're going to pass this to standard out, so we can then pipe this time into rwstats so we can get a statistical view of what we're pulling back here. And then for what we want percentages on, we want source IP and destination IP. And then for the values, we're going to pass in the records, bytes, and packets. So just to make our lives easier, I'm just going to copy this command. If I can type, let's do a quick clear, and then we'll paste that in, run that. And you can see we have the statistics now and the data to back us up on how these IPs are communicating with each other, specifically on port 53. And you can see 50% is going to that 243 and about 50% is coming back. So we're getting pretty much even traffic back and forth from these two addresses here. So again, putting that together, pretty much 99% of the DNS traffic occurs between those two addresses, which is a lot of DNS traffic. And it's kind of abnormal unless one of these hosts is a DNS server, and I don't think it was specified that any of these are. Even though the traffic volume doesn't represent ordinary traffic, let's view the frequency of the request, because that's going to give us some more granular information. Even though we're looking at it at this high level, we can take a look into some other metrics, right? So we can look at the actual time that these packets were sent and the frequency involved, because that could also point to some abnormal stuff as well. So in this case, we want to specify the specific address. We can do that with source address here over port 53 as the destination port. We're basically going to pipe that into rwcut, and for the fields, we want the source, the destination, as well as the time, because we're going to do some frequency analysis here. We will simply run this, and you can see here we have all of the source IPs here, which as expected, that 221, and they're all going to the destination of 243. And if we look at the time here, we don't really have much difference. You can see it's all within this same minute. It's just the seconds. So, we have seconds off here. So 44, 45, couple in 45. So it looks like twice a second this communication is being done. And again, this is kind of a red flag. So we have over 10 DNS requests in less than a second. Again, this is definitely something that we want to write down and keep in our notes. So let's sort of flip this and look at the other IP address using the same command. So in this case, all we need to do is just replace the IP address. So we're just passing in that .243 address there. We're going to run that. You can see actually we have nothing. We have no output. So why is that? Well, so in this case, it means that the second IP address that we checked didn't send any packets over the DNS port. There's definitely something weird going on here, which we can look a bit deeper in. So before we conclude the DNS analysis, let's look at the remaining connection pairs. So let's check the host that we marked as suspicious. So this .221, and let's see if any other hosts on the network have interacted with it. To do this, we're basically just going to pull in any address that communicates with our suspicious IP address. We're going to pass that to standard out, put it into rwstats, because we want to pull the percentage or the stats of any fields that, any communication between the source and the destination IP. So I'm just going to copy this again. And you can see pretty much 100% if we add this up of the traffic, or 99 point whatever, is all between this 221 and that 243. But you can see there are two records. So these two here at the end. We have this 205.213.108.99 address communicating with our .221 suspicious address here. So this is one more IP address that we should be aware of because it was communicating with our suspicious one here. So let's focus on this new pair by overviewing the communicated ports to identify the services. Okay, so let's filter in that .99 address. Let's pass into standard out and look at the statistics for what it's communicating with, right? Okay, so if we pass in this command here, so if we run this, you can see pretty much what the 205.213 address was communicating with, and it's all on port 123, or the network time protocol port, which is kind of benign in this case. There aren't too many records, like there's just one record or two records here, and it's all over just that network time protocol, which is kind of normal. In this case, we don't need to focus on it as much, just something to keep in the notes. So with our analysis so far, we've revealed the potential command and control server, which is happening over DNS. So with our detection notes, we have Detective Frosto here. The communication pair that uses the DNS port is suspicious. Yes, we've identified that. And there's a sign that there's a C2 channel because of the frequency that we saw of that communication, as well as just, how much volume there was. So the source IP address that ends in 221 sent massive DNS requests in short intervals. So we should analyze these now at the packet level using that deep packet inspection, or more PCAP analysis, to get more detail on the actual payloads or body of these packets. So according to the flows, the destination address has a higher chance of being the DNS server. This means that the source address might be an infected host communicating with a C2. And the big question here is, did we find Tracy McGreedy's C2 channel? Well, let's continue the analysis to discover if there are any more anomalies. So remember that using our quick statistics command here with rwstats, we discovered the massive volume of DNS traffic. If you remember back when we ran this first command here with the rwstats, looking at the destination ports, we also saw 14% was HTTP traffic, which is kind of abnormally high if you look at the rest of the sample here. So with this in mind, we can now dig into the port 80 traffic to see if there's anything else abnormal going on. So we're just going to filter based on any packet that is going over port 80. So destination or source, doesn't matter. Let's just grab port 80, and we're going to run the statistics on this so we can pull out the source and the destination IPs so we can see which communication pair is going on, or which source is communicating with which destination, and so on. So let's run this here. Okay, interesting, and it's kind of tricky to notice. So you can see this .235.223 is communicating with this .236.223. You can see 50-50 pretty much. So these are communicating back and forth. And these are the only contenders here. So We've listed the connection pairs that created the noise. Let's reveal the one that created the load by focusing on the destination port. Okay, so now we're just going to get a bit more specific and look at the destination. Okay, so now that we filter on every IP address that is communicating over port 80, you can see that this 236.223 is the one that's sending the most traffic here. So now that we know what the suspicious IP address is that's communicating over port 80, we can do a little bit more digging here. Again, this is NetFlow analysis. We don't have the payload, so we can't see the request details, but we can look at patterns, and we can look at behavior. So let's do this. Let's view the frequency, again, kind of like what we did with the DNS, but let's also look at the TCP flags of the request to see if there are any abnormal patterns. So to do this, we're going to provide a couple of filter arguments here. So we're going to specify that suspicious IP address. We're going to pass that into rwcut to read out the output. And we're going to just look on the fields for source IP, which is going to be the suspicious IP, the destination IP, as well as, importantly here, we want the TCP flags of the actual connection, as well as the time or the frequency. And then we're going to pipe this to head because we're going to get basically a lot of output. So we only want to limit it to the top 10 lines that we get. So that's why we're piping it to head. So we run this, we get the results. But if you remember, what we could also do instead of head is just provide the numRex argument, and we can just set that to equal to 10. We're going to get the same thing here. So just two ways to do that. You can use, standard built-in Linux commands, or you can use the argument here to pull back a specific limit, in this case 10. So what do we see here? We see some interesting things. Obviously, this 236.223, our suspicious IP here, is communicating to 235.223. But you can see here the time. Again, this is like within the same second. You see, we're just milliseconds apart here between each request. So this is a lot of requests in the same second. Obviously, something abnormal here, something suspicious. And if we look at the flags, we just see S here. And what that means is it's just the SYN flag that was turned on in this request here. So when you think about the TCP protocol, well, you think about the three-way handshake. So let's say we have our two machines here. This one's our suspicious IP here, so we can just write suspicious on this to identify it. And let's just say this is a web server. Typically, when you make connections, the client is going to send over a SYN packet. That's going to be that S that we saw. And once receiving that, the web server is going to send back what's called a SYN ACK. So if the server is willing to establish that connection, it's going to reply with that SYN ACK, which is basically an acknowledgement that the SYN was received. And then lastly, if all goes well from the client side, it's going to send back one final, again, this three-way handshake, which is going to be just an ACK. And that's just going to be the final acknowledgement from the client before the actual connection is established. So again, a series of SYN packets sent in less than a second needs attention and clarification. Absolutely. So let's view all of the packets sent by that host first. Okay, so let's run this command, which is basically we're going to filter on that IP address. We're going to look at the statistics for the source, the flag, and the destination IP. And what we're looking for here is to see if that three-way handshake was completed. So are we getting an ACK back from the suspicious IP? So let's run this command here. And you can see we're getting no results. We're just seeing that SYN flag. We're getting no ACK. We're not getting any of that third stage in the TCP handshake. So again, this pattern is starting to look suspicious because why are they sending a SYN but not an ACK? That means the connection is not completing. Why is the connection not completing if there's all of these connections in a row within the same, second? One possibility is that they're doing some sort of scan, like an Nmap scan. They're doing like a SYN scan where, again, it's not going to complete that ACK because it's going to be a bit quicker or a bit stealthier. But the other option is maybe they're doing a SYN flood, which is a type of denial of service attack. And seeing the frequency of these requests is definitely alarming because it kind of does at this point seem like there's some sort of denial of service going on. But what we can do is take a look at the answers to confirm this from the web server or from the second IP that's receiving all of these requests. So let's run this command here. And assuming our suspicions are correct, we're going to see a lot of SYN ACKs going on here. You can see here the flags, the SA for that SYN ACK. You can see all these records are replying with the SYN ACK. So again, this is expected. When a web server receives that SYN request, they're going to reply with a SYN ACK, assuming communication is available. The suspicious thing here is that it's supposed to send the ACK packets back to the web server after the SYN ACK, and that's what we didn't see when we filtered for it. That's definitely a red flag, and again, a DDoS or a SYN flood attack is quite apparent here. So again, we will elaborate on this in our detection notes, but we still need to check if the host has interacted with other hosts on the network using the following command. So again, let's pass in that suspicious IP address, and let's look at basically any network traffic, and we want to pull back the source and the destination IP to see if anything else was interacted with. And luckily, we're not seeing any other IP addresses here. It's just that suspicious IP going off to that web server, and then the web server replying back. So again, yes, luckily there were no further interactions with any other IP addresses, so we can conclude the analysis and elaborate on findings in our notes. The communication pair that uses port 80 is suspicious, yes, and there's a sign of a denial of service attack. And the way we come to that conclusion is that the source IP address that ends in the 236.223 sent a lot of TCP SYN packets in short intervals, which we saw. The suspicious address never sent that ACK request to complete the three-way handshake. And because of this, there's a high probability that this is a SYN flood attack. So the question now is basically who's behind that denial of service and why? And is the host compromised? Do we have an insider? We definitely need to take a look at the host now and see what's going on. For a conclusion, well, we're not there yet. I think we might have skipped a couple questions by accident. So what is the number of bytes transmitted by the top talker in the network? Yes, okay. Okay, if you remember this command, we are taking a look at the rwstats, and we are looking at the fields for the source IP. And we basically want to see which IP address is communicating the most on the network, and that's going to be this .243 address here. And for the number of bytes, you can see we have 735,229. Paste that in there. Excellent. What is the S time, or what is the source time value for the first DNS record going to port 53? Okay, so for this one, we can do rwfilter. We want to pass in our log here, and we want to look at port 53 specifically. And then we're going to pass this into rwcut to read the lines, and we want the S time value. So what we can do, S time, and then we want to basically limit it to, well, I guess the top one, right? So we can do num rex equal 1. In this case, we have this S time here, or this starting time, and that should be the correct way to format this. Yeah. Okay, what is the IP address of the host that the command and control server potentially controls? So we found this out basically by looking at the rwstats tool, and we were looking at which source and destination IP pairs were communicating the most. So we'll just run this with a count of 10, and we can look at the top result here where the source was that 173.221 communicating with that 238.243. So I'm going to copy this IP address here, and it wants it in defanged format. So defanged format is where you have these brackets around the dots, and you'll often see this with IP addresses or domain names or URLs. And the reason being is that some systems might translate this automatically as a hyperlink, and you don't want to do that if it's suspicious IP or a domain. So we put these brackets around them to basically break off that potential. So you can also just do a search for CyberChef. If you have like a list of a bunch of IPs or domains you want to defang, as it were, we can paste that in. And if we just search defang, you'll see there's one for URLs as well as one for IP addresses. So I'll just drag over the IP address. We will get the output there, if you can see that. And we can just paste this in. Hopefully will be the right answer. There we go. So which IP address is suspected to be the flood attacker? Okay, so we just went over that. And the way we figured this out was basically by looking at all of the port 80 connections. And then we pass that into the statistics so we can look at which fields under the source, destination, and the destination port. And with this, we saw that this IP address here was the one communicating most over port 80, which in this case was the one that was sending the SYN flood. So we can paste this in here and I guess manually defang this one and submit that. And you can see we got the correct answer. And for this last question here, what is the sent SYN packets number of records? Okay, so I guess how many SYN packets did the attacker send? In this case, we can look at our previous command here, and all we need to do is look at the records column, and that's going to be 1,658. So let's just move that over to here. And there we go. That is pretty much it. We can now read the conclusion here. So congratulations, you have helped the Santa's Security Operations Center team identify the network traffic statistics and report the potential anomalies to McSkitty. In this task, we have covered the fundamentals of the network traffic data and analysis process. We have also explained the two standard network data formats, so PCAPs, network flows, as well as the differences between them, the pros and cons, and we demonstrated how to analyze network flow data using the Silk suite. Now, practice what you've learned by answering the questions below, which we have done, so well done. So now that we've done all this analysis, if you want to delve deeper into network packets and network data, you can look at the Network Security and Traffic Analysis module, which is another great module that contains all sorts of information on the core concepts of network security and traffic analysis, covering things like Snort, as well as Zeek, different tools here, Brim, Wireshark. So this is a perfect module if you like this kind of thing, or if you want to learn more about this kind of thing. So we can just hit completed there, and we should be good to go for this task. So well done, everyone. Thank you for sticking along and hanging on. We learned quite a lot through this task, and I hope you enjoyed it and had fun. I sure did. And I hope you enjoy the rest of Advent of Cyber. Stay tuned for the remainder. There's going to be a lot of fun stuff coming out, and I hope to see you there.